Let's unlock the full potential of your statistical analysis and gain confidence in the results you obtain from large and complex datasets. In statistics, assumption testing holds the key to ensuring the validity and reliability of the conclusions. By carefully evaluating whether key assumptions are met or not, we can avoid the pitfalls of misleading results. I will demonstrate how assumption testing can be seamlessly integrated into your analysis with the help of the STATA software. I will also use an example utilizing time series data that spans over a specified period. Among the various regression methods applied to time series data, the ordinary least squares or OLS regression stands out as the most commonly employed. Its primary objective is to establish and quantify relationships between variables present in the dataset. However, it is essential to acknowledge the utmost importance of conducting assumption testing before proceeding with the OLS regression. The verification of specific critical assumptions, namely stationarity, normality, heteroskedasticity, multicollinearity, and autocorrelation, plays a pivotal role in ensuring the accuracy and reliability of the regression results. Starting with my example, assume we want to assess the impact of macroeconomic factors on the current account balance of India. The data is from the period 1993 to 2022. There are multiple variables like current account balance, GDP, private investment, government expenditure, trade openness, trade balance, external debt, fiscal deficit, FDI net inflows, foreign exchange reserve, broad money supply, rate of inflation, rate of interest, and exchange rate. To start, the first step is to create a data file in STATA. For this, either import the Excel sheet or copy and paste the data in the data editor. The first row of the data will be treated as the variable names. As the data spans over a long period, that is, 1993 to 2022, we will declare it as time series. Set the time variable as yearly by using the command tssetYear yearly. Now, test stationarity of the data by applying the Dickey-Fuller test. For this, apply dfuller to the variable name with lag 0. So, our command will be dfuller current account balance, lag 0. This will compute the stationary value for the current account balance at the level test. For our study, let's set a significance level of 5%. This means the p-value, which is a measure of significance, must be less than 0.05. However, in our case, the p-value is 0.4254. This is higher than 0.05. To fix this, we need to adjust the variable's form and try again. To make the data stationary, we use a process called differencing. This process helps to remove non-stationarity. We repeat this differencing test at various levels until we achieve stationarity, which means the p-value becomes less than 0.05. To start, we will compute the first difference value using the command gen_dca equals d.current account balance. dca is the new variable created to store the first difference value of the variable current account balance. Its p-value is 0.0001, which is less than 0.05, so the data is stationary. Follow this procedure for all the variables, that is, GDP, private investment, government expenditure, trade openness, trade balance, external debt, fiscal deficit, FDI inflows, foreign exchange reserves, broad money supply, rate of inflation, rate of interest, and exchange rate. At first, when we tried to make the variable broad money supply stationary by taking the first difference, it didn't work, as the p-value was 0.99. This is significantly higher than 0.05, so we applied a second difference and called this new variable ddbm. After the second difference, the p-value became 0.00. This means the variable broad money supply is stationary. Now that we have achieved stationarity, we have other assumption tests to perform. But before that, we need to create an OLS regression model. To do this, we will use a command where we specify the dependent variable followed by the independent variables. The command will be reg dci dgdp dpi dg dto dtb dd DFD, DFDI, DFE, DDBM, DI, DIM, DID. Next, we want to understand the differences between the actual data and the values predicted by our model. This will help us assess how well our model explains the variation in the data. To do this, we use the command predict residuals. This will calculate the residual values and create a new variable called resid in the data editor. The next test we want to perform is to check if our data follows a normal distribution. To do this, we use the skewness and kurtosis test. Here's how to perform the test. Go to Statistics, click on Summaries, Tables, and Tests. Then select Distributional Plots and Tests. Choose Skewness and Kurtosis Normality Test. In the dialog box that opens, select the variable name resid, which represents the residuals we calculated earlier. Click on OK to run the test. After running the normality test, we will get the results. The values for PR kurtosis and PR skewness are both higher than 0.05. Even, the significance level of the test is 0.17. This signifies that we cannot reject the null hypothesis of normal distribution. In other words, the data is considered to be normal. The next assumption test is to check for heteroskedasticity in our data. We want to show that our data does not have heteroskedasticity. To do this, we use the command STATA, HETTEST. The p-value obtained from the test is 0.02, which is less than 0.05. Normally, a value of 0.05 or less indicates heteroskedasticity, but in this case, it's the opposite. To deal with this, we need to calculate robust standard errors using the command BCE_robust after regression test. This helps us handle any issues with heteroskedasticity in the data. Therefore, the updated regression model will be reg, DCA, DGDP, DPI, DGE, DTO, DTB, DED, DFD, DFDI, DFE, DDBM, DI, DIM, DIE. BCE robust. However, this new model cannot calculate the value of heteroskedasticity. This can only be used to remove heteroskedasticity. Next, we conduct the autocorrelation test using the Durbin-Watson test. This will help us check for any correlation between the data points. Use the command DWSTAT for this. Afterwards, we perform the multicollinearity test using the variance inflation factor, VIF. The VIF helps us assess any high correlation between the independent variables in the model. Use the command VIF to run this test. From the results, we find that the variable DED has the highest VIF value of 129.25. This indicates that DED may be highly correlated with other independent variables in our model. Thus, the variable is removed and another robust, standard error-based model is developed. Reg, DCA, DGDP, DPI, DGE, DTO, DTB, DFD, DFDI, DFE, DDBM, DI, DIM, DIE. VCE robust. After modifying the model, all the VIF values for the variables are less than 10. This is a good sign, indicating low multicollinearity. Additionally, the Durbin-Watson statistic has a value of 2.57, falling between the range of 4-DU and DU at a 5% significance level. This means there is no serial correlation present in the dataset. Since we have fulfilled all the necessary assumptions in our dataset, we can confidently conclude that, without considering external debt, we can assess the impact of macroeconomic factors on the current account balance.